All right, going to open up your textbooks to page 221. You had just 3 questions from your reading last night, questions 23, 24, and 26. Didn't have time yesterday to start our discussion of heat, but we'll get into that today. And let's go and take a look at these questions. Question 23, this is something we'll get into more tomorrow, but what are the heats transferred at the melting point and boiling point called? Michael?
The heats transferred at the boiling and melting points are called heat of fusion and heat of vaporization.
Or if we took them respectively, melting point is heat of fusion and boiling point is heat of vaporization. Also referred to as the latent heats of fusion and vaporization. And that's the reason why number 24 says, what are L sub F and L sub V for water? L stands for latent heat. L sub F being latent heat of fusion. L sub V being latent heat of vaporization. What is the latent heat of fusion for water? Audrey? Number 24.
333 joules per gram.
Good. And then the latent heat of vaporization, Kendall, the other half of number 24.
2,260 joules per gram.
Good. 2,260 joules per gram. Let's see. Number 26. What equation embodies the law of heat exchange? Let's go back to Audrey.
The equation which embodies the law of heat exchange is Q equals MC delta T.
That's the equation for heat itself. What about law of heat exchange? What did you have, Kendall?
I had Q over T equals Ka times delta T over delta X.
Okay, that's for heat transfer through a body. Michael, what did you have for number 26, the law of heat exchange?
I had the same thing as Kendall.
Oh, okay. Now here's what threw you off. Because they talk about the law of heat exchange before they talk about latent heats of fusion and vaporization. So the questions went out of order. But if you flip back to page 215, you would see the law of heat exchange. Under the cute little picture of the little girl is like, I'm getting cold. And their smart alecky brothers say, no, you're getting less hot. Anyway, right under there, law of heat exchange. And if you look at equation number 14, that embodies the law of heat exchange. And you see there in bold at the top of the next column, equation 14 is called the law of heat exchange. So if you did your homework reading before we try to answer the questions, we would have seen that already. If we try to just look up answers instead of doing our reading, tricky Abeka people. So anyway, questions on that. Sure, we're doing the reading, not just answering the questions. All right, next thing in your notes. Yesterday we took a quiz over temperature, right? Fahrenheit, Celsius, Kelvin. We talked about thermal energy and thermometers and how changes in temperature cause thermal expansion, all that stuff. That's all been talking about temperature. Temperature is the measure of thermal energy. It's measured in degrees or kelvins. What we're getting to in this next chapter is actually heat. Heat is not the measure of thermal energy, it is the transfer of thermal energy. A transfer of thermal energy. I have thermal energy in my body, and I touch something cold, less thermal energy, and thermal energy flows out. You remember talking about exothermic and endothermic reactions in chemistry? Exothermic is one that feels warm to the touch because you are absorbing energy out, or energy is leaving, Energy is leaving, energy out of. Exothermic feels cold because energy is going out of the reaction. Endothermic, I believe, is the one that feels warm because energy is going in. Maybe I should stay in my lane and not touch chemistry. I think I might have this backwards. Anyway, but the point is thermal energy is flowing, right? So I grab this thing. It feels cool to the touch because thermal energy is flowing out of me and into it, correct? I am transferring my energy to this object. Now, I'm not transferring in the sense that we did in chapter 11 where I'm pushing it or throwing it, right? We talked about a transfer of energy that way. This is just thermal energy. But it's still like work in a sense. It's thermal work, if you will. I'm transferring energy from one body to another. It's just not evidenced by motion. But there is a flow of energy, right? There's an energy level state that changes. So if we want to, we can think of heat kind of like work in that sense. And so heat, for our purposes, will be measured in a unit that we're familiar with, joules. Heat is going to be measured in our class in joules. Now, that's not the only unit we could use for heat. The book mentions a few others. We, in fact, had a homework question the other day that asked about that. This heat can be measured often in the scientific community in what are called calories. Now, of course, when we hear calories, we usually think of food. Food's calories are actually kilocalories, or thousands of calories. But calorie is a measure of energy transfer. The food has energy in it. We eat the food. We get in those calories. Our body has energy, right? So are calories bad? Not if you use the energy. The problem is if you don't use the energy, right? And then, of course, health class, right? It turns into glycogen and then eventually fat and, carbs bad. Why? Well, carbs wouldn't be bad if we burned energy, right? Y'all know who Michael Phelps is? Olympic swimmer, more gold medals than just about anybody out there. I think he had a 10,000 calorie diet when he's doing his training. Actually, 10,000 calories. Well, he's burning so many calories, he has to. When I was in high school as a cross-country runner, I was in great shape. I took in 4,000 calories a day. I needed to, otherwise I wouldn't have the energy to run. I needed lots of carbs. I looked for carbs. Bagels were great, pasta's great, pizza's great. Right, anything with carbs, give it to me. Why? Because I need those carbs, because I'm going to burn them immediately when I'm running mile after mile after mile. The problem was, I don't run anymore. And I still like carbs, but I don't run anymore. So I get energy in, and I don't spend the energy in. Gain weight. All right, anyway. But calories are just energy, right? It's energy that can be transferred from the food to you. Calories in the same way could be transferred thermal energy from one body to another. Calorie, here's the definition of a calorie. A calorie is the amount of heat required, or thermal energy transfer, right? The amount of heat required to raise a gram of water. The amount of heat required to raise a gram of water, 1 degree Celsius. So imagine instead of having a whole bottle of water, we're to take just a single gram and we're to put it on my finger. Once the temperature of that gram of water has gone up 1 degree Celsius from touching my finger, which transfers the thermal energy, 1 calorie of heat has been transferred. Okay? That's the amount of heat required to raise a gram of water 1 degree Celsius. Now, a couple little side notes you don't have to know with the definition. This assumes normal atmospheric pressure, 1 atmosphere. Technically, I believe it's 14.5 to 15.5 degrees Celsius is the specific 1 degree Celsius change. It's 1 degree Celsius, okay? Gram of water, 1 degree Celsius, we call that a calorie. We should note that a calorie is 1,000 calories. Calorie with a capital C is 1,000. I say 1,000, I read 100. 1,000 calories. So it's not a separate unit to know we're a kilocalorie. Just know that when you see a capital C, that's what it's implying. So don't write capital C if you don't mean it, right? All right, there's another unit we could use, and that is the BTU. Now, if you've, maybe family's heater has ever gone out or you've had to buy a portable heater or something like that, you'll oftentimes see the output, the heat output, if you will, in terms of BTUs. So many BTUs this heater puts out. That's about the only time you ever hear it because it's not really used in science anymore. BTU stands for British Thermal Unit. And so the British, of course, when they were first coming up with these, they've since gone the way of all other nations. They're not special anymore. But the British, when they came up with this, they weren't dealing in grams and such. What did they deal with? Pounds and ounces. And the British go big or go home, right? A pound of water. And what is this Celsius nonsense? 1 degree Fahrenheit. And that's your definition for a BTU. The amount of heat required to raise a pound of water, 1 degree Fahrenheit. Amount of heat required to raise a pound of water, 1 degree Fahrenheit. Amount of heat required to raise a pound of water. Why not an ounce? Better go home, I guess. A pound of water, 1 degree Fahrenheit. That's a BTU. Again, technically, I believe it's 63 degrees to 64 degrees Fahrenheit. Whatever, it's 1 degree Fahrenheit, okay? Let's keep life easy, okay? But a British thermal unit. Again, that's assuming normal atmospheric pressure as well. Because again, pressure does affect temperature and things of that nature. Where does the joule fit in then? Well, a joule's already been defined. We've already come up with the joule. In fact, we're going to have to flip ahead just a little bit here in your books, and I didn't write the page number down, and I should have. Page 224, so just a few pages over. James Prescott Joule, the one who came up with this unit, joule for energy transfer, actually came up with this where he used weights, there's your force, and as the weights would move up and down a certain distance, okay, so there's your force times distance, there's your work, there's your joule, how much energy was transferred into the water. So he has these two oscillating weights that drive these little paddles back and forth. As the paddles stir the water, what are they doing? They're moving the water. As the water's moving, it's gaining more kinetic energy. We call this kinetic energy thermal energy. And so it was able to raise the temperature of the water, or the thermal energy of the water, 1 degree Celsius with a certain amount of work being done. So that's how we can make an equivalent of heat to work, in a sense, was through that. So what we'll do is we'll just memorize this fact, that a single calorie is equal to 4.184 joules. So you get the idea that a joule is very, very small. It takes 4 plus joules to make a single lowercase c calorie. The joule doesn't have a definition unto itself because it was already devised for work. But we can make the equivalency for heat, noting that 4.184 joules equals approximately equals a calorie. Questions on the different units we'll use as we talk about heat. Again, temperature, thermal energy, that's degrees Celsius, degrees Fahrenheit, Kelvin. Heat, the transfer of energy, that's calories, BTUs, and joules. Make sense? Questions on that? Now, obviously, the units are based on pure water. Why? Because pure water is readily available, it's easy to purify, whatever. But what if we had other materials? What if I wanted to raise the temperature of this lab table 1 degree Celsius? What if I wanted to raise the temperature of a lab stool 1 degree Celsius? For instance, you ever sat down on a really cold seat? It's like, oh. Maybe car seat. How many have leather seats in your car? Okay. And seat warmers or no seat warmers?
No.
No seat warmers. Okay, we're not cool like that either. We did rent a car once, our car was being fixed, so the company fixing the car gave us a rental SUV to use. It had seat warmers. It was the one day it snowed last year. It was on a Sunday. I don't know if you remember, but it was on a Sunday, and it suddenly started snowing. These wet chunklets, clumps of snow falling from the sky. It's pretty cool. We had the SUV at that time. It had seat warmers. Big fan of seat warmers. And then we had to give them back their fancy SUV, and we got our minivan back and no seat warmers. But anyway, leather seats, right? Cloth seats, they stain. Leather seats are cold. In the summer, they're hot. Okay, but anyway, what if we wanted to raise the temperature of the seat, the cold seat, 1 degree Celsius? Well, the heat required to raise the temperature of a body, of an object, is what we call heat capacity. The book mentions it's represented by the capital letter C, as in capacity. Don't even worry about that because you're not going to use that anyway. But heat capacity is the heat required, or the transfer of thermal energy required, to change the temperature of a body, of an object, 1 degree Celsius. Well, you think about it, like, let's just say a body is like this lab table. Well, over there we have similar lab tables off to the side, right? But they're smaller. Doesn't it make sense that one of those little lab table thingies, one of those little lab carts over there, is going to be easier to change its temperature than this one? Why would that be? It's smaller, right? If we wanted to raise Kendall's temperature 1 degree versus Michael's temperature 1 degree. Audrey always gets left out of these discussions. She sees the happy medium. But if we wanted to change the temperatures, right? It would be easier to change her temperature because she's smaller. They're made of the same stuff, right? Skin, bones, muscle, blood, whatever else is in you people, okay? Right? The stuff that's in us, biology, okay? Well, you have the same stuff, but she's smaller. So it's going to take less thermal energy. If we had a stick takes less thermal energy transfer, less heat to raise its temperature than an entire tree made of the exact same stuff, right? Similarly, a broom handle made of plastic and the same size broom handle made of wood are going to require different amounts of heat. Every single object, pretty much, is going to have a different heat capacity because every object is pretty much unique. Now, all 9 of these lab tables in here are going to take the same amount of thermal energy, so they all have the same heat capacity. All 18 stools have the same heat capacity, right? But unless you're... Can you imagine trying to make a chart of heat capacities? That'd be silly. What would be easier would be, okay, well, all of these lab materials are made out of oak wood. What if I took a single gram of oak wood? What's its heat capacity? That would be really easy to calculate, wouldn't it? And then we simply say, okay, well, how much oak wood is in this table? How much oak wood's in that cart? How much oak wood's in this cart, right? And now you can begin to find heat capacity more easily if you know specifically how much heat is needed for just a gram of a substance. Okay, a pine tree, 1 gram of pine wood. What's the specific heat? Okay, now we've got this whole tree. We can kind of do the math. Versus, here's a stick from the pine tree. What's its mass? We can figure out how many grams it has. So heat capacity, the heat required to raise the temperature of a body or of an object 1 degree Celsius, really not helpful. What we have called specific heat, much more beneficial. Specific heat is the heat required to raise 1 gram of a substance, 1 degree Celsius. Heat capacity is the heat required to raise 1 gram of a substance, 1 degree Celsius. 1 gram of Kendall, 1 gram of Michael. Roughly similar body composition. Okay, not exactly identical. I would assume Michael's more muscular. He better be. All right, right? But roughly the same substance. So if we took, just on average human flesh, about how much the specific heat would be. Okay, for a gram of that, the specific heat. It's calculatable. And in fact, if you were to Google specific heats, you could get a massive table of lots of all kinds of different substances that people have analyzed. How much thermal energy transfer or heat is needed to raise 1 gram of that particular type of material, that substance, 1 degree Celsius. Now, where kids get hung up, this sounds a lot like the definition of a calorie, doesn't it? Heat required to raise 1 gram of water, 1 degree Celsius. Heat required to raise 1 gram of a substance, 1 degree Celsius. Calorie is a unit based on water. Specific heat could apply to any substance, but what is the specific heat of water? A calorie, 4.18 joules, roughly, if you're looking at the table, right? Because specific heat takes a single gram of a substance. If it's a gram of water, you've got the definition of a calorie. So if you're looking at definitions, right, you're thinking about, okay, quiz question. If it's based on water, that's a unit. Calorie is based on a gram of water, 1 degree Celsius. BTU is based on a pound of water, 1 degree Fahrenheit. A gram of a substance, that's the specific heat, the heat that is specific to a particular substance. Make sense? We're going to notate specific heat with the little letter C, and I add a subnotation SP. I like using subnotations just because it helps me keep track of what's what. So C sub SP, not sure why I have different sized parentheses there. It's bothering you too? Specific heat, C sub SP is what I'll use to notate that. But think about it, the specific heat required to raise a gram of a substance, 1 degree Celsius. So if we were to try to make an equation of this, don't write this down yet, heat required. We need a letter to represent heat. H? No, somebody decided we'll use that for enthalpy. Not entropy, but enthalpy. You might remember that from last year. So we can't use H. Man, all the letters seem to be used. There's one we ain't used yet. Haha, Q. So we're going to allow Q to represent total heat. You do go ahead and jot that down. Q represents total heat. Just jot that down for now. So if we have a certain amount of heat that's required to raise a gram of a substance, 1 degree Celsius, we would have to divide the heat needed to raise a body, 1 degree Celsius. We have to divide that by how many grams we have and how much temperature change took place. And if we do that, we'll get our formula for specific heat. Don't write that down. Because why would we calculate specific heat? They've already done that on Google. They have all the specific heats listed out on massive tables. Why would I ever calculate that? But what I might do, if I had, for instance, say a cast iron skillet, I can find the mass of the skillet pretty easily. I can figure what temperature change I want the skillet to have. Maybe it's at room temperature, which about 20-ish degrees, 68 degrees. How many keep your house around 68? How many colder than 68 in winter? How many warmer than 68 in winter? What's your house at?
70 and mid-70s.
Mid-70s? Yeah. So we're, on the really cold days, we'll go down to 67. Before we had kids, we'd go all the way down to 66, but kids don't do well with 66. So anyway, so let's just say the cast iron skillet's around 60, around 20 degrees Celsius, and we want to, raise the cast iron skillet to, cooking stuff, cooking temperature. That would probably be around 100 degrees Celsius, right? Maybe higher than that even. So we can find the temperature change we want. We can calculate the mass of the object we want. We can look up the specific heat on a table. What we really want to know is how much heat has to flow into that thing. How much thermal energy transfer has to happen to get the skillet up to that temperature. So usually what we'll do is we'll actually say that heat needed equals the product of these things when we cross multiply. And if you would, write this down as the heat equation. If we're representing heat as Q, Q equals C sub SP M delta T. That's our heat equation. Obviously, delta T, like before, it's got to be in degrees Celsius. It's got to be final minus initial, right, for temperature change. Mass, if you'll jot this down, has to be in grams. Because the specific heat is based on grams. It's like, whoa, counterintuitive here, right? We're used to taking grams. Oh, gotta make it kilograms. No, it's the other way around. You got kilograms, you gotta make it grams. Because the specific heat, if you look at page 214, I believe it is, we have a small table of specific heats. We don't have the massive pages and pages of it because we don't need it. We will use substances from this chart, or if I make up my own problems, I will look up the specific heats for you. So specific heats, notice the units at the top. It's in joules per gram times degrees Celsius. Well, if the temperature changes in degrees Celsius, that cancels with per degree Celsius. Grams with per grams, that's where we'll get our heat in joules, which we already said at the beginning. All right? So look, if you would, at the example problem across the page, page 215, example 14.7, and readeth that for us, Kendall.
How much heat is required to raise the temperature of a 227 gram aluminum cooking pot from 25 degrees Celsius to 105 degrees Celsius?
So this is like a little saucepan or something, and you're raising the temperature of the pot. Now, there's nothing in the pot. If there's anything in the pot, that messes with the math. Why? Because the pot's temperature can't go up without also affecting the temperature of whatever's inside it, correct? Thermal equilibrium is going to be maintained. But we just have a pot, we put it on the stove. Anyone ever done it? Put the pot on the stove, turn on the stove, forget to put anything in? Anyway, that's how people burn water. Pour the water in later. Boil it all out. I've never actually burned water. I don't know. I hear about people burning water. Audrey, you've burned water? You have to tell me about it sometime when it's not on camera. We won't put you on the spot that way. So we have a certain amount of heat that has to flow into our aluminum cooking pot. All right? We don't know how much heat. But we know it's an aluminum cooking pot, and aluminum heats differently than other materials based on its own specific heat, the amount of heat needed for every gram of aluminum to go up a degree Celsius. We know we have 227 grams we have to deal with, and we're raising it from about 77 Fahrenheit, so our houses on a summer day, right? Assuming we keep our houses warmer in the summer than we do in the winter, right? So 77-ish, okay, we're around there. And we're raising it up to 105 Celsius. We're raising it a little over the boiling point of water. And the question is, how much heat do we need? Well, look across the page, find aluminum on the chart. What is aluminum's specific heat?
0.910.
0.910, okay? So 0.910 joules per gram times degrees Celsius. Multiply that, it's 227 grams, right? Again, if they gave you kilograms, what would you have to do? Go back 3 places, right? A kilogram's 1,000 grams. So if they said 0.227 kilograms, I would have gone to 227 grams. And then the change in temperature, 25 degrees up to 105 degrees. What is it? 80 degrees Celsius. Again, degrees Celsius and grams cancel with the pers and all that. You multiply it out, 0.910 times 227 times the 80, and how many joules of heat will be needed?
60,525.6.
And don't be shocked by the big number. Remember, I said a joule is tiny. A calorie is not that big. Thermal energy transfer, like, is it going to take that much to make a single gram of water go up a degree Celsius? No. A calorie is already pretty small. That's why food calories are measured in kilocalories. And a joule is less than 1/4 of a calorie. When we get our numbers in joules, they're going to be huge numbers. So don't be fazed by it. You might want to go kilojoules here, right? Take off the 3 decimal places and say it's 6, is it 3 sig figs? It's 2 sig figs. So we'll say 17,000 joules, or you could say 17 kilojoules, just to diminish the size of the number. Questions on that example? All right, flip over, if you would, to page 221 now and do problem 13. Page 221, do problem 13. Oh, read problem 13 for us first. There's one little annoying thing that they worked in here. Audrey?
How much heat must be added to exactly 1 liter of water at 25 degrees Celsius to bring it to the boiling point 100 degrees Celsius?
You know what they didn't do? They didn't give us the mass. They said it was a liter. Have you ever looked at one of these little bottles of water? 16.9 fluid ounces? It's a half a liter. It's 500 milliliters. And what's interesting is a milliliter is a gram. So if it takes 1,000 liters to make a liter, it takes 1,000 grams to make the kilogram. A liter is a kilogram. So that's in fact how they kind of defined the gram, and all of that was based on water. So if you'll cross out 1 liter and put a kilogram instead, a kilogram of water. So we've got a kilogram of water. Ignore the pot that it's in. We're trying to boil this water, get it to the boiling point at least. Is it 25 degrees Celsius? We want to get it to 100 degrees Celsius. How much heat is needed? At your seats. Using the heat equation. All right, if you're not finished with number 13, go and pause the video, give yourself time to finish. We're finished in here, though. So let's take a look at number 13. And what's the equation we use to calculate heat, Michael?
The equation used to calculate heat is Q equals C sub SP m delta T.
There we go, where we'll plug in for the specific heat. It's water. What's the specific heat of water, Kendall? 4.18 joules per gram times degrees Celsius. Like, that should be an easy number to remember if you memorize 4.184 joules to make a calorie, because the specific heat of water is a calorie, so 4.18 joules makes sense. The mass of water, it says is a kilogram is what I told you to change it to, but we don't really use a kilogram, Audrey.
1,000 grams.
1,000 grams, of course grams and per grams cancel, and we're bringing it from 25 degrees Celsius up to the boiling point, which is 100 degrees Celsius, so that temperature change there, Michael, is
75 degrees.
75 degrees Celsius. Of course, the degrees Celsius and per degree Celsius cancel. We multiply these numbers together, and again, it's going to be an enormous number of joules needed. What do we get for our answer here, Kendall?
313,500.
Good. Initially, 313,500 joules. We do need to account for sig figs. It looks like we got 3 sig figs we're allowed to use here. 314,000 joules, or we could say 314 kilojoules. Either answer would be fine. Or 3.14 E5 joules would work as well. How many of one of those answers for number 13? All right, pretty straightforward equation. All right, flip back if you would to page 216. And we talked about thermal equilibrium before, and now I use the example of shaking hands with the elderly lady at church who's got the cold hands. You're shaking her hand, and your body continues to generate body heat, right? Until you're dead, your body continues to make more thermal energy within itself. It will warm you. By the way, have you ever noticed, anyone ever gone to bed and maybe you realize later you were a little underdressed? Maybe you should have been wearing a sweatshirt and sweatpants and you were in shorts and a t-shirt or something, and your body gets really hot afterwards. You ever noticed that? Your body's trying to manufacture heat to keep your body warm and actually overcompensates in some cases. I noticed I was having a hard time sleeping because it kept being so hot in the middle of the night, and I thought, natural thought is, I'm overdressed, I'm wearing too much clothes, but I'm like, I'm in shorts and a t-shirt, I should be fine. I realized after the fact, no, my body's overcompensating. I put the sweatshirt on, I wasn't nearly as hot at night. Okay, because your body manufactures its own heat. But let's just assume, rather than things that make their own heat, let's just suppose we have a cold chalk holder, we drop it into a cold bottle of water. I'm not going to do that because I'm not ruining my bottle of water. I need that. Eventually, the two will reach the same thermal equilibrium, correct? Same thermal energy. How does that happen? Because the water gives thermal energy to the chalk holder, or vice versa, depending on which one's warmer, right? If I were to heat this up, maybe hold it in my hand for a bit, warm it up, drop it in there, the transfer takes place, and if it's insulated, if there's no energy losses to the surrounding environment, however much heat the one object loses will equal the same heat that the other object gains, correct? We call that the law of heat exchange. So in your notes, law of heat exchange. It's not a difficult concept, I don't think, to grasp, right? The same would be true with monetary exchange, right? If Michael's like, you know what? I really want to help my fellow seniors out. I'm loaded. I'm rich. He's not actually, I don't think. Maybe he is. And he's like, I've got lots of money, so I'm going to give money to these ladies here because I'm just a really nice guy and I want them to vote me class president. and of 3 people. Anyway, so he gives money to seniors. Well, realize, however much money you gain collectively equals the money he loses. That's just how it works. Unless he's got a printing press at home, and then that would be like my body continuing to manufacture heat. It's pretty straightforward. That's how anything works. That which something gains is that which something else has lost. So we could say that Q lost by one body equals Q gained by the other if the heat exchange takes place in an insulated system. Well, that's almost true. Remember, a loss of energy, how do we indicate losses in physics? Negatives. Gains would be positive. Will a negative ever equal a positive? No. But if I made this negative Q loss, that would give me the double negative, wouldn't it? So here's the equation to know. Negative Q lost equals Q gained. Negative Q lost equals Q gained. And that way the sign conventions work out the way that they should. Now how do we apply this? Page 216, I told you to turn. Read example 14.8, and let's kind of follow this example problem through. Kendall, read the example problem for us, if you would, please.
A 95-gram block of copper is taken from a furnace and dropped into a 410-gram glass beaker containing 120 grams of water. Both the beaker and the water are at 15 degrees Celsius. After the system reaches thermal equilibrium, the water is 35 degrees Celsius. What was the temperature of the furnace? Assume that no heat is lost from the beaker.
Now that's a stretch, isn't it? Right? If you ever had a pot of boiling water and you set it down on a hot pad, and you take the pot off and you feel the hot pad, it's warm. We're assuming no heat escapes from the beaker into the surface it's sitting on. Okay, that's not possible. You ever put your hand near a pot of hot water or something, there's heat that radiates upward. We're assuming that doesn't happen. So it's a bit of a stretch here, but we're going to assume a perfectly isolated, insulated system. And there's 3 things that are talked about. First of all, we're introduced class, there is a block of copper that's been sitting in a furnace, so it's really, really hot. Then there's a glass beaker, and inside the glass beaker there is water. Okay? Picture it. You got glass beaker, you've got water. Assuming the water sitting in the beaker, since they're in contact with each other, assuming they've been in there for any length of time, the two should have the same temperature, the same thermal energy, correct? Then you got this block of copper from a furnace plunked inside. What's going to happen with the thermal energy? It's going to flow from the block of copper into the, and therefore from the water it'll flow into the beaker, which technically then it should also radiate to the air around it and down to the surface, but we're ignoring all of that, okay? That's what should happen. The 3 objects in question, 2 of them are gaining thermal energy, are gaining heat. Who's gaining heat here? Water and the beaker. Who's losing heat? The copper. I'll just say C. All right, so we've got copper losing, we've got water and beaker gaining. For each Q in question, we're going to use the heat equation, CSP M delta T. So we can say, but this is negative, remember? So we're going to say negative CSP M delta T. That's for the copper. Equals positive, because we're on the gain side, CSP M delta T, that's the water, plus CSP M delta T, that's the beaker. Does that make sense? And we just plug in all the heats that are lost on one side with negatives, all the heat that's gained on the other side with the positives. We just plug in the numbers and let the algebra take over. So copper, flipping back, what is copper's specific heat? Flip back a page. What's copper's specific heat, or 2 pages technically, 214? 0.390. We already know how the units work out, right? We're okay if I don't write the units because I'm lazy. The mass of the copper, how much mass was there?
95 grams.
95 grams. And the temperature changed. What temperature did it end at?
35.
Everything reaches equilibrium at 35. So that's the ending temperature minus, what was the initial temperature?
15.
Of the copper? That's what I don't know. However hot it was while it was in the furnace, right? So I'm going to just represent that T sub I. Does that make sense? Let's go to the water. Water's specific heat.
4.18.
4.18. The mass of the water. How much water was in the beaker? 120 grams. And the temperature of the water ended at 35 like everything else, right? It was equilibrium. What did it start at? So what's the temperature change? Positive 20 degrees. Let's go to the beaker. It's a glass beaker. So split back. What is glass's glass? Yeah. What is the specific heat of glass? 0.84. I'm going to talk about glasses. All right, let's see. The mass of the glass beaker.
410.
How much?
410.
410. Wow, so it's a big beaker with not much water in it. And the temperature of the beaker started out at 15 like the water did, but it went up to 35. So its temperature changes also 20. Do we understand the layout here? It's not just a bunch of numbers that should confuse us. We just take everything that's losing heat, CSVM delta T, with a negative. Everything that's gaining heat, CSVM delta T. Hey, there's two things gaining heat. Okay, another CSVM delta T. We just plug in the numbers. Now, let's start with the easy side, because there's no variables over here. So on your calculator, let's just multiply these three things. 4.18 times 120 times 20. How many joules of thermal energy transfer occur into the water? 10,032 joules of heat are absorbed by the water. Okay, what about the beaker? How much heat goes into the beaker? I just mistyped something. What do we get?
6,888.
6,888 joules. All right. So if we wanted to, we could go and get the total energy gain, or heat gain, excuse me, going on the water and beaker side. How much total heat is gained by the water and beaker collectively? 16,920 joules of heat gained by the water and beaker. That must be the total on this side as well then, but I've got a binomial. You know what we have to do with the binomial? Distribute. Let's just multiply these two numbers, 95 by negative 3.9, or 0.39. And what number are we distributing right here?
Negative 37.05.
All right, that gets distributed into the binomial. I told you, let the algebra take over. So that's what we're doing is algebra. Multiply the negative 37.05 times 35.
Negative 1,296.75.
And then distribute negative 37.05 times negative t sub I.
Positive 37.05.
T sub I, right? What do I have to do to get the t sub I by itself? Again, we're solving the equation, just following the algebra.
The 1,000 to the other side.
Move that over by making it a positive. Add it to the 16,920. And we should be up to 18,216.75. And then to finish getting the t sub I by itself, divide the 37.05. And apparently, what is the initial temperature of this copper block before it's dropped into the water?
91.66.
Rounding off to sig figs, I believe they gave us, it was 2 sig figs everywhere, so. And temperature will be measured in degrees Celsius. Heat in joules, temperature, degrees Celsius. That's really hot. Questions on that? Again, it's a lot of numbers. It's a lot of writing. If you're looking at this, like, what in the world? It looks like a complicated problem when you look at it in the textbook, doesn't it? But it's really pretty straightforward. Just a lot of math on the calculator and following algebra. Questions on that? Let's look at one more so you'll be prepared for your homework this evening. Stay with me through the bell. Number 9. Going to read 14.9, excuse me, the next example problem. Audrey?
A metal cylinder weighing 920 grams at 100 degrees Celsius is dropped into 500 grams of water contained in a 150 gram iron cup, both at 13 degrees Celsius. If the temperature rises to 35 degrees Celsius, what is the specific heat of the metal cylinder?
All right, in this problem, class, what is losing heat? The metal cylinder, whatever metal it is. And what's gaining heat, class? The water it's dropped into and the iron cup with it, both things. So on the losing side, we have a random piece of metal. On the gaining side, stay with me, we have water and we have the iron cup, okay? And so for each case, we have to find how much heat was lost from the metal, how much heat was gained by the water, how much heat was gained by the iron. Every time you need to know heat, class, we use the heat equation. What is it?
Q equals
CSP m delta T. So for the metal, don't forget the negative here, negative CSP, whatever the metal is, m, whatever the metal's mass is, delta T. Then for the water, CSP m delta T. Plus for the iron, CSP m delta T. Now, the metal, it doesn't tell me what kind of metal, and it doesn't tell me the specific heat. In fact, that's what it tells me to find. So I'm finding this specific heat here. It does tell me the mass of the metal, 920 grams. Remember, if they give you kilograms, make it grams. It says the metal started out at 100 degrees Celsius, but it all ended up at what equilibrium temperature? 35. So it went from 100 degrees down to 35 degrees. What's the temperature change? Negative 65 degrees Celsius. Do you see what's going to happen with the pair of negatives here? They're going to cancel. In fact, we could simplify this side right now if we wanted to. 65 times 920 real quick.
59,800.
59,800 CSP. All right, now let's come over here to the water. Water specific heat, do we have it memorized yet? 4.18. How much mass was there of the water?
500 grams.
500 grams? All right, and the water started out at
13.
and went up to,
35.
what's the temperature change?
22.
22. Let's get the water's heat gain real quick.
45,980.
45,980. All right, got some confirmation. Plus, let's go to the iron cup. I have to look that one up because we don't know that one yet. Iron's specific heat.
0.47.
0.47. All right, how much was the mass of the iron cup?
150 grams.
Only 150 grams, so small cup. And, well, iron's pretty heavy, or dense anyway. And then it also started at 13, went up to 35 too, right? So it also had a temperature change of
22.
22, all right? So multiply those numbers. Much smaller value here.
1,551.
1551.
Yes.
Add the 1551 plus the 45,890. Or 980, excuse me, I'm dyslexic, 980. And then we have to do what? Divide out the 59,800. And apparently, this particular metal has a specific heat of
0.7948.
0.7948, blah, blah, blah. Is it two sig figs again?
Yes.
Yes. So we'll say approximately 0.79. And remember, that's going to be joules per gram times degrees Celsius. Look at that specific heat table real quick. Is there anything on there that's around 0.79? No, aluminum's higher than that. Copper's way smaller. Gold is ridiculously smaller. Iron, lead, they're all smaller. So this is something lighter like aluminum versus the heavier metals. Maybe something like tin, perhaps. I don't know. But some unknown metal that we have there. Your homework for tonight, you're going to do 3 problems. One of them is just a straightforward heat problem. The other 2 are going to be heat exchange. Page 221, problems 14, 17, and 19. Page 221, problems 14, 17, and 19. On number 17, ignore the container. On number 17, the container doesn't exist. So here, remember, we have the metal on one side and the water and the cup. On number 17, for some reason, they ignore the container. So it's just the 2 substances, one's gaining, one's losing. All right, have a wonderful rest of your day, and you are dismissed.